Pluto is a distant and cryptic diminutive planet that was once a member of our planetary family. However, recent astonishing declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a dazzling disclosure. They suggest that this icy world is on a potential impact course with Neptune. Yet how could this happen, and what might be the consequences of such a significant event? Are we witnessing a rare galactic phenomenon, or is there more to this impending cosmic impact? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partly due to its unusual orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's path is dangerously close to Neptune's. Both Tyson and Kaku are sounding the alarm about a potentially hazardous impact between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astounding 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets, and this tilt and eccentric nature add layers of complexity to its orbital pattern. One of the most captivating aspects of Pluto's orbit is its intersection with Neptune's path. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its unusual trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves understanding how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this issue illustrates how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms alpha libration and longitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In Pluto and Neptune's case, this term means that whenever Pluto crosses Neptune's orbit, it's positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from intersecting. Longitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated well above their orbital plane, providing an additional layer of protection from potential collisions. Another fundamental aspect in this scenario is the VZK oscillation, named after scientists von Zeipel, Chi, and L.V., who studied how objects move in space. It describes how three celestial objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity, which affects their movements. For Pluto, the VZK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's orbit appears chaotic, this oscillation helps keep it moving smoothly. Understanding its orbit is truly important. It gives us a clearer picture of the solar system's dynamic nature. The situation of Pluto shows that even the most seemingly unstable orbits can achieve a state of balance through the intricate interaction of gravitational forces and orbital mechanics. This also illustrates the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the peculiar nature of celestial bodies, and Pluto's orbit is a perfect example of this eccentricity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's path on its initial conditions, is remarkably demonstrated in Pluto's case. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term trajectory. In the vast expanse of our solar system, Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its composition and behavior. One of Pluto's most intriguing features is its surface, a complex tapestry of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided unprecedented data about this distant world. Pluto's surface is characterized by vast plains, towering mountains, and deep valleys. One of the most notable features is the Sputnik planitia, a large heart-shaped plain primarily composed of nitrogen ice. This region displays a diverse array of land features, including massive ice blocks and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active despite its great distance from the Sun and low temperatures. Its atmosphere is primarily made of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is weak but exhibits fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interaction between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies share an orbit around a point in space that lies between them, rather than Pluto merely orbiting Charon. This unique relationship contributes to the intricate gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper belt. The Kuiper belt, a region beyond Neptune populated with small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, providing scientists with a glimpse into its formation. Pluto's orbital characteristics could offer insights into the movement patterns of these distant objects, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One of the significant implications of understanding Pluto's orbital dynamics is the potential impact on our